Rajkumar Nagarajan from Lumentum, and the topic of my talk is ROADMs at the edge of the network. The edge of the network is that part of the wired infrastructure where the traffic pattern is mainly north-south. There is zero to very little east-west traffic between the nodes that form the edge loop, and most of the traffic is hub to spoke. Now, depending on which part of the geography you are from or which operator you are, you may call this part of the network as the access loop or the collector ring or the feeder loop. Now, with the advent of 5G services and content caching and edge computing, the edge of the network is seeing a plenty of unplanned traffic growth. We know that a ROADM-based network works very well when traffic patterns are unpredictable. But the ROADM economics, which are currently optimized for metro solutions, simply do not price in at the edge. And this talk, we explore the elasticity that exists between cost and features to enable an economic transition of the edge towards a ROADM-based architecture. Let's look at the different flavors of the edge networks currently deployed. The most commonly deployed ones are ADMs or add-drop multiplexers or packet optical boxes that take in sublate data at 1 or 2.5 gig and multiplex them on to a 10 gig line rate to feed them into the metro edge aggregation point. Now, when the ring capacity is exhausted, you would light up another ring and stack it on top, either by commissioning another fiber or employing a CWDM fiber on the same ring. Similarly, you would also find OTU4 muxes, which have coherent line ports that take in 10 gig traffic from the various service clients and feed them back into the metro. And as before, when any section of the ring is exhausted, you will have to stack another set of boxes, which makes this architecture highly inefficient in a scenario where new or higher service rates are required to be onboarded on a regular basis. It quickly becomes apparent that an all-optical approach to the edge is the best way to go. Today, the optical approach followed is to deploy a FODEM solution or fixed optical add-drop multiplexers built with either dielectric filters or AWG. You can have 40 or more wavelengths channels in the ring with fixed amount of add-drop capacity in each of the sites. Now, FODEMs suffer from two main issues. You need to have an a priori knowledge of the traffic growth pattern so that you can allocate the add-drop capacity between the sites accordingly. As you bring in new channels at the different sites, optical power balancing between the express and the add-drop becomes an operational headache, as there are no mechanisms that allow you to equalize the channels. Both these issues are solved by using a ROADM-based edge architecture if one can achieve comparable network economics. Now let us look at the different ROADM configuration that exist in today's metro deployment. Route and select architectures with a 2x20 WSS or a twin 2x32 WSSs are the benchmark to support high degree counts and enable a CDC type add-drop structure. By CDC, I mean colorless, directionless, and contentionless type add-drop structure. Each degree is built out of a separate blades with all the other functional elements like an optical channel monitor, a preamplifier, and a booster all built into it. This is a feature-rich configuration, and consequently, it comes also with a relatively high price tag. The next approach is a broadcast and select configuration used mainly for nodes with low degree count. Here, the WSS is only used on the add side, and the drop is achieved with passive splitters. This configuration supports both colorless and directionless in the add drop. It is moderately economical compared to the configuration in the chart above. Now let's examine a third type of configuration. By utilizing a twin module and using each of the WSSs in a MUX configuration for the add and using a splitter couplers for the drop, we can build a 2-degree node on a blade. A configuration like this is well suited for the edge, where economics dominate the narrative. Let us examine the edge ROADM and apply a set of practical boundary conditions in order to develop a low-cost design. Now, optical transparency between the edge and the metro is very key to eliminate OEO conversions and reduce the overall network ownership cost. Now, the metro operates on a flex grid with the provision for variable channel widths depending on the baud rates used. So the edge, in order to maintain the optical transparency, would also have to support a flex grid operation in the C-band, and also have the provision for variable channel width for a seamless optical handoff. Now, the metro is expected to support up to 16 degrees. But in the case of the edge, most of the nodes are expected to be 2 degrees with the possibility of a maximum of 4 degrees for some future mesh connectivity options. The metro also needs to support a 30 dB span loss. In the case of an edge, given that these links are going to be small, I mean, they could be relaxed about 14 dB. In addition, the spectral occupancy in the C-band is around 4.8 terahertz for the metro. And in the case of an edge, that could be relaxed to 2 terahertz. Now, what this gives us is it can give us up to 8 terabits of feeder traffic in the ring to home back to the hub. And as we saw previously, a ROADM degree needs additional monitoring functions and which are performed by optical channel monitors. Now, these OCM devices will do a fast scan of the channel powers at all the different common ports. Now, if we are to say relax the scanning speed requirements, we can embed many of the optical channel monitoring functions inside the WSS modules for a very minor expense, resulting in a much lower overall solution cost. In the previous slide, we looked at the set of feature sets that we defined for the edge that are different from that is there in the metro, and this new set of feature set will allow us to design a more cost-optimized solution for the edge. So in this chart, we will try and quantify what those relaxed feature sets have given us. So what you see here, the leftmost candle here is the baseline cost of what our metro ROADM degree is. And when you take that solution and then you apply the first level of optimization, where you say that I'm going to support, the edge is going to support a spectral occupancy of 2 terahertz and span losses that are not more than 14 dB, you're able to simplify the amplifier designs and bring the overall solution cost to around 75% of where you started out with. And then if you apply the next lever, which is saying that I don't want to use a standalone OCM, and I'm willing to live with a slower scan speed, albeit with the same level of fidelity as what my standalone OCM gives you, you end up with a solution cost that's around, I would say around 55 to 60% of where you began. And now let's take the next leap of faith and say that instead of building a degree on a blade, we're going to build a node on the blade. So I'm going to have 2 degrees on a given blade. And once you do that, you end up with a cost point that is less than 45% of where you started out with. Now, this is a fairly compelling price point. Out here now, we are almost in the forum territory. In the previous chart, we suggested that we would like to build a node on a blade as opposed to building a degree separable solution for the edge. Now, one could make an argument saying that by building a node on a blade, I'm reducing the overall system availability, and by introducing a single point of failure. So what I propose to do is actually try and look at the numbers that come out and actually quantify what are we foregoing by building a node on a blade. Now, when you look at the solution of a degree separable or two independent node blades, the line card fit is around about 1,000. And this is again based on 10 years of field data for a ROADM blade. So if one degree fails, the traffic can still be routed through the other degree, which makes the effective fit of this particular solution around 500, which calculates to an MTBF of 228 years. And if you look at an integrated degree solution, given that there's more electronics in it, you're going to get an overall fit of around 1,200. And if this line card fails, both the east and west are affected. And the MTBF calculates out to be around 95 years. Now let's look at the network availability of a 4-node edge link in the two scenarios, one degree separable or an independent line card, and the second with integrated degrees or having a node on a blade type of a solution. And in this calculations, all I am looking at is only the fit contributed by the equipment at the different sites. I'm completely neglecting any fit due to the fiber plant, even though in real world scenarios, the fiber plant fit will dominate all availability calculations. Now, for a 2-degree separable, the total link fit amounts to around 2,000, giving you a total MTBF of around 57 years. And for the node on a blade or 2 degrees in a given card solution, you end up with a total link fit of around 4,800, giving you an MTBF around 23 years. And given that this is the edge of the network, and we can assume that the mean time to repair is 12 hours. If you take that, what it amounts to is the network availability for a degree separable solution is 99.997, and that for an integrated 2-degree solution on a blade is 99.994. There's hardly any difference between these two numbers. Now, why this is happening is because the actual field fit numbers of an LCOS-based WSSs are incredibly low. So given that, it actually enables us to build multiple degrees on a given blade for the edge application. In conclusion, some of the key points I would like the audience to take away with them are that ROADMs at the edge will enable an organic growth of the network to support future high capacity applications, both planned and unplanned. By building the edge with FlexGrid based WSSs, one can achieve an optical transparency between the edge and metro, eliminating costly OEO. The edge solutions need a very dedicated approach, different from the solutions utilized in the metro designs. By doing that, one can leverage the feature versus cost elasticity and provide a path for a low edge economics. Building a purpose-built edge ROADM solution will result in a much lower total cost of ownership for the service providers. I thank you all very much for listening to this talk. And if you have any questions, please feel free to reach out to any one of us at Lumentum, and we'll be more than happy to answer your questions.